Hi everyone, welcome to our first online module. So starting this week, all of the modules that we cover on a weekly basis are going to be online, and the structure of the modules would remain the same, where you're going to have an overview page which will discuss the learning objectives of the module. It will cover the reading. Hi everyone, welcome to our first online video lecture. So for this video lecture, the topic is going to be unbalanced transportation models. We started off with chapter 5 right before spring break, and we were able to cover the first example under chapter 5, which was for a transportation model for executive furnitures. I'm going to quickly revise some of the network characteristics of a network model, and then we'll jump off to the second example, which is an unbalanced transportation model. Just to revise some of the concepts in chapter 5, we started off with network flow models by describing some of the applications of network flow models. In this particular chapter, there are 6 applications which are discussed in detail. They're listed here in the slide in front of me: transportation models, transshipment models, assignment models, maximal flow, shortest path, and minimal spanning tree. Each of these models have a bunch of applications in real life, and we'll go over examples of where these models are used in real life, so that you can get an idea of how to apply these models once you learn how to solve for them. So we covered transportation models in class, face-to-face, when we started off the chapter. We are going to move on next to transshipment models, and then follow the same sequence of topics. I will provide a short video for each of these examples, which you can watch and then compare it to the Excel file which has been uploaded in order to check the solutions and practice for the solutions on your own. So for the transportation model, since we covered the basic concepts of transportation models in the face-to-face class, I'm not going to repeat that. Instead, I will cover an example for an unbalanced transportation model. That will be the first example that we cover in this video lecture. The remaining video lectures are going to talk about each of the other 5 network flow model applications. Network models are special because they are mainly accompanied with a network diagram that help us identify our decision variables and identify what type of node each node is. So in a typical network model, you have both arcs and nodes. The arcs represent the path or the assignment of one entity to another entity, whereas the nodes can either be origin nodes or destination nodes. Origin nodes are also known as supply nodes, and destination nodes are also known as demand nodes. Origin nodes can be something like a factory which produces products, so this is where all the production happens, whereas demand nodes are consumption nodes. This is where all the consumption happens. We also have a third type of a node, which is called a transshipment node, and we're going to cover that in detail in the transshipment example. But transshipment nodes are special because they have the characteristics of both the supply node and the demand node. That means products can be shipped into the transshipment node so that they act like demand nodes, but products can also be shipped out of the transshipment node so that they act like supply nodes. So a typical example of a transshipment node is a warehouse. For example, Amazon, for Amazon, a company like Amazon, the origin node could be the original vendor or seller of the item. They typically send their product to a warehouse, Amazon's own warehouse, and then from there it is shipped to the customer. So the Amazon warehouse serves as a transshipment node in this example. The network diagram that we create for each example is going to help us identify the decision variables. The decision variables are the number of arcs that you have in your network diagram. Now, make sure that you make the distinction between unidirectional arcs and bidirectional arcs. Unidirectional arcs are the ones that only flow in one direction, and bidirectional arcs are the ones that flow in both directions. So there might be cases if you have a bidirectional arc in your network diagram, you might have to include two decision variables in order to account for that arc, because one decision variable is going to cover one direction of flow and the other is going to cover the reverse. For each node, we typically write down an equation which is called a flow balance constraint equation, and the equation is net flow is equal to the inflow minus the outflow of the node. Over here, make sure that you identify your nodes as either supply node, demand node, or transshipment node, because that is going to help you identify what the correct right-hand side value for your constraint equation is going to be. We also established the fact earlier in our face-to-face class that the constraint coefficients for these network flow balance equations are either going to be 0 or 1, unlike previous examples that we've done before. And if you're inputting the values in your model as integers or whole numbers, your results will automatically come out as integers or whole numbers. So let's take an example for an unbalanced transportation model. The network diagram that you see in front of you in the video here is for a balanced transportation model. And the reason why this model is a balanced transportation model is because if you count the total supply on the left hand side, which is equal to 700 for this particular example, it's exactly equal to the total demand, which is again 700 units for this example. Now, in a case like this, it's easy to come up with your constraint equations using the balance equations that we introduced earlier. But if the situation was such that the supply was not equal to the demand, and that could mean the supply for any of these factories could change from what is given here to something else, whereas this demand stays the same. So that is an example of an unbalanced transportation model when the total supply is not equal to your total demand. So here's the case when we changed the executive furniture example from the original balanced model to an unbalanced model. The whole model remains the same except for this one change in the input variables, where the old demand for the node at Albuquerque was 300. It has now been changed to 350. If that change takes place, what that will do to our model is that now the total supply is going to be less than the total demand, because the total supply would be equal to 700 units, whereas the total demand now equals 750. Now, in order to deal with an unbalanced model, we're going to follow the exact same procedure that we followed for the original transportation example. The only change that is going to happen here is that earlier all of the network flow balance equations had the equal sign in there. But now, because supply is not exactly equal to demand, and in fact it's less than demand, then we would have to change our three demand node constraints from equal signs to less than or equal signs. Now, this is the only change that you would need to make for a situation like this. Let's take a look at what this change does to our Excel template. This is the Excel model that we had built for our original transportation example. Des Moines, Evansville, and Fort Lauderdale were supply nodes, whereas Albuquerque, Boston, and Cleveland were demand nodes. Over here, we're calculating the total flow out of each of these three supply nodes by calculating the sum of each row. And down here for the columns, we're calculating the flow into each of these into these demand nodes by calculating the sum down the column. Now, in our original problem, we had our balance flow equations such that all of these were the equal sign. But for an unbalanced model, especially for this example, the demand is higher than the supply, which means that your demand cannot be exactly met. So you would have to change the signs for the demand constraint nodes to less than or equal to, as opposed to what we had earlier, which was the equal sign. That's because the demand is higher than the supply, so the solution cannot meet the full demand since the supply is lower. After making this change, you're going to run solver again. However, that does not change the original solution that we had. That's because this is still the optimal cost despite these constraints changing and despite the demand increasing. The reason for that is you only have limited capacity and your cost is associated with that capacity. You cannot go beyond that capacity, which is why the optimal solution still remains the same. If we reverse the scenario, and instead of increasing the demand, we increase the supply such that we change the capacity of one of these nodes. In this case, the supply node for Des Moines, the capacity for that has been changed from 100 to 150. Again, this is still an unbalanced model, but the situation has reversed where supply is more than the demand. So for a situation like this, when your supply exceeds the demand, the constraints that you need to change the sign for would be the supply nodes, in this case Des Moines, Evansville, and Fort Lauderdale. And instead of having an equal sign in there, you're going to have a greater than or equal sign because your supply is eventually going to be higher than the demand. You need to allow for that in your Excel formulation as well. So in the reverse example, when we increased the capacity for Des Moines from 100 to 150, I will make that change and reverse my demand constraints back to equal. And instead, I will change my supply constraints to greater than or equal signs here. So as a rule of thumb, you can remember this, that when supply exceeds demand, you change the supply node constraints to greater than or equal to. And when the demand exceeds supply, you change the demand nodes to less than or equal to. And this is going to be true for majority of the situations.